All right, so the final lecture for this week, we'll discuss sedimentary structures. And so kind of building off of what we learned about bed forms in the previous lecture, sedimentary structures are a huge component of stratigraphy, and they are the observable features that are left behind in the stratigraphic rock record as a result of the movement of particles and arrangement of particles into patterns based on deposition or erosional surfaces. Okay, so they typically result from the coherent arrangement of particles based on their composition, i.e. density, or by size, or by shape, or by orientation if they have, if they're angular, like I mentioned before, for platy particles, they might get imbricated, right? So as flows move across the landscape and bed forms operate and so forth, particles will get arranged or sorted based on those components, right? Based on their properties, okay? And this organized framework of these grains that gets left behind can be referred to as stratification. So in this image, you can see here that, if this had all just been one uniform grain size, you would maybe not see anything of interest here. But because the grains were sorted by size, you can see surfaces that are generated here. This was an erosional surface, right? You can see depositional surfaces. These would have been cross beds formed probably by a dune avalanche face, right? And you can see the coarse particles are being sorted out at the base of these beds, and then you get fining of those particles and so forth. And compositional maybe results in these dark bands here. Those might be, denser particles or lighter particles, depending on the system. I think those are probably biotites, so they might be hydrodynamically, a little bit easier to move. And so you end up with the grain size or the grain sorting or the grain shape sort of organizing in such a way based on the hydrodynamic processes that are going on that can result in stratigraphy being formed or stratification being formed that you can actually see in an outcrop at some other later time. Okay, and there's a ton of different types of structures that we can talk about. I'll give you some examples of each of these. So we'll talk about bedding and lamination. We'll talk about graded bedding. So that's the variation of particle size, sort of like a consistent variation in particle size. We'll talk about cross bedding, ripple marks, sole marks, mud cracks, raindrop impressions, soft sediment deformation, and trace fossils. And so we'll go through all of these in a little bit more detail throughout this lecture. Okay. So we'll start off with bedding and lamination, and this occurs as the dynamic sorting of grains based on either their composition, size, shape, or their orientation in a flow or as they settle out of suspension, and they result in sort of planar features that can be observed based on the changes in shape or size or orientation or composition, right? So in this case, you can see the composition is, there are maybe clay minerals or something like that are sorted from the quartz grains, or the size might be silt from sand, right? And in some cases, it's the shape where, the spherical or the more equant particles are settled out here, and then the platy particles came along and were, flattened out on top. Similarly, you can get orientation like this, where there's imbrication that defines a layer, and so forth. And so this is sort of how you get layering or bedding and lamination based on the different particle properties as they move through a flow. Okay, and we define the bedding versus lamination using these scales. I will say that when I say them verbally, I'm usually pretty approximate, but these are the actual thickness definitions that describe, just like you have grain size classification schemes, we have bedding versus lamination classification schemes. And it's based on about a 1 centimeter difference. Smaller than 1 centimeter defines laminae or lamination, and greater than 1 centimeter describes bedding. Okay. And so this looks in planar bedding situations, which can result from either lower stage plane bed flow, like we talked about in the last lecture, or upper stage plane bed flow. In either case, you can get planar lamination. You can also get it from just pure settling. And it looks like this. You just have long, parallel, planar beds that are sort of distinct from one another by either grain size or slight sorting variability. And oftentimes you can't, if it's like sandy or silt, oftentimes you can't even tell what that variation was just by visually looking at it. Oftentimes it can be just a slight change in the grain size or sorting, which changes the permeability of the sediment, which changes how much fluid moved through it after it was deposited, and therefore how much cementation it got or what type of cementation it got. And that changes how the surface weathers, which is why you get this sort of undulating effect here. That's a typical reason why you see bedding and lamination when you go up to an outcrop, is changes in the slight changes in permeability based on sorting is a pretty common one. Okay. In this case, you can also see what's called a parting lineation. So if this was a function of plane bed flow conditions and there was flowing water moving across these, the grains of sand will end up sort of getting lined up in these little stringers, if you will, based on little turbulent vortices, and you'll end up as the surface gets parted. If you see the rock and you break it apart a little bit, you'll see those little stringers moving in one direction, and it'll look kind of like this. You can kind of see that there's sort of an overall pattern in how the rock pulled apart. This is looking down on a surface here in this image that's sort of left to right oriented, and that's called parting lineation, and that can actually be really helpful in telling you the plus or minus 180. You can't tell if it's going this way or this way, but you can tell it's going either this way or this way, flow direction in the past. Okay, so that's why that's relatively useful to understand. So similar to bedding, to planar bedding, you can also get what's called graded bedding, where you can visually see a pattern of fining or coarsening through time or upward in the stratigraphic section, right? As lower beds are deposited first, and then you get younger as you're adding more sediment, right? Certain types of changes in transport conditions or certain types of depositional environments can result in a steady gradation from, in this case, coarse to fine, right? That repeats itself, right? So this is a coarse bed that fines upwards, and then you get what appears to be an erosional surface here, and then the process starts over again, where you go from coarse to fine, and then you have a nice sharp surface here, and then coarse to fine, and then a nice sharp surface here, and so on. Okay. This is common in a lot of situations, and so it's important to note because it can be really useful in understanding what type of depositional environment you're looking at. And we'll talk more about that when we start talking about specific environments. Okay. Then there's cross-stratification. And cross-stratification occurs by the movement of topographic features like bed forms, bar forms, delta fronts, etc., that result in deposition of strata that cross horizontal surfaces, right? So in this case, as the bed forms migrate, you have those lee faces, the avalanche faces at the front of these bed forms where the sediment is being deposited at the angle of repose, right? So at a 30-something degree slope. And then as, subsequent bed forms come by and erode at their scour, in these scour pits at the front of these bed forms where it's an erosional feature, then you might get an erosional surface that cuts across those non-horizontal cross strata. Okay, and it's the sort of the original non-horizontal nature of those strata that make them referred to as cross stratification, so that they'll cut across the horizontal surfaces that might get formed by other processes. Okay, and that's incredibly common. And can result from a number of different processes. Like I say, you can get them from bed forms like ripples, dunes, anti-dunes, cyclic steps. You can get them on the faces of bar forms, right? So you might have bar form cross stratification with superimposed bed form cross stratification, because you can have dunes on the backs of bars, but you could also have ripples on the backs of those dunes, right? So you can see that you can get multiple scales in even one deposit of cross stratification. They can also occur on delta fronts and a whole bunch of other places. Okay. So this is what that might look like in outcrop. So you can see, again, this is an image from a coastal dune. So this is a beach dune in this is the Parkman sandstone in Wyoming, where this is from Teapot Dome. If anybody remembers from their high school history class, the Teapot Dome scandal, this is the Teapot Dome oil field that was named for. So these are cross beds. Here you can see the erosional scour here, and then you can see the cross bedding compared to the original, more or less horizontal bedding plane that would have been here. Okay. This is what that looks like in an aeolian or wind-blown system. So these are cross beds in an active aeolian field or a dune field. I don't recall, a colleague of mine took this, I want to say this was Great Sand Dunes, but I could be mistaken. But you can see, again, you have the erosional features here. These are the bounding surfaces they're often referred to, the erosional scour between dunes, sorry. And then you can see the cross bedding here from the avalanche faces of these dunes. Okay. Here's another example of that from closer to home. This is from the Bonnet Carré spillway upriver from us here in Louisiana on the Mississippi River. These are the deposits from the 2019 flood that opened up the spillway and deposited a bunch of sand in there. And you can see these are dune scale cross stratification again. But in this case, the variation that results in the visible cross strata is by particle type. So the density of these grains is different from quartz sand, which is the lighter colored stuff, to coal dust, which gets blown into the river along coal terminals that ship coal along the river here, which has a slightly lower density. Okay, and so that makes these beautiful surfaces visible. And so these are the avalanche faces, the lee faces of those dunes, right? And then these are scour features here. Okay, so that's cross stratification. In certain special circumstances, when these dunes that are producing cross stratification are in an aggradational system, so if the sediment that's being deposited on the bed is being deposited quicker than the dunes can migrate downstream, you get these really cool features called climbing ripples, where oftentimes the entire dune shape or ripple shape is preserved. So you can see here you have the whole stoss side, lee side of each individual bed form being deposited and being preserved in the rock record, and that's because the bed is aggrading, or there's so much sediment coming out of suspension that the bed is aggrading faster than those bed forms are migrating downstream, and so you don't, instead of getting erosion off the back, you're actually getting deposition from suspension. And so these are called climbing ripples, and they're really cool to see, and that can tell you that the bed was in a highly aggradational state at that time, and so therefore probably not in an equilibrium condition. Right? Here's what one of those looks like in a modern deposit. Again, similarly, it's compositional differences that highlight these bedding orientations in this particular case. Again, you can see almost the entire, for most of these, the entire bed form is actually preserved. So you can trace along an individual bed and see multiple ripples or dunes preserved here, right? So if you trace out that bed, you get the Stoss side, the lee side, the next Stoss side, the next lee side, and so on. Okay, so those are climbing ripples, and those would be referred to as supercritically climbing ripples because the whole bed form is preserved. The next feature or class of feature that we can talk about are what are called soul marks, and they're referred to as soul marks because they are present on the bottom of beds typically, and they're markings on the bottom of coarse bedding that reflect the erosion that occurred of an underlying deposit by either currents or tools. So if you see these, it's typical you'll see a muddier unit, for example, or a finer grained unit overlain by a coarse grained unit, which tells you that, say, there was a slow current or no current at all that resulted in the deposition of this mud, and then as the current speed increased, say as a flood occurred or a turbidity current occurred, the current speed increased such that you could erode out this pre-existing fine layer, and then you ultimately started to deposit coarse material on top of that. And so either the flow resulted in the erosion in the case of what are called flute marks or flute casts, you'll hear them referred to, which look like this, or there might be tool marks, which also occur as, say, a pebble or a coarse grain rolled across and scoured out that underlying deposit here. So with flute casts, the way this happens is that you get focused erosion of that bed by turbulent eddies, right? So you get an eddy that starts to scour out a hole in that underlying bed, and it scours it out with the steep side on the upstream side and the sort of gentle side on the downstream side, just like this. And they're pretty useful in that they are, unlike parting lineations, they provide unambiguous evidence for the flow direction, right? So in this case, the flow was from the steep side down to the shallow side, okay? And so this is what one of those might look like in an outcrop. So you're looking up at the bottom of a bed in stratigraphic position world. These may be tilted beds due to tectonic forces, but you're looking at the bottom of the bed and you can see that this was the upstream side and this was the flow direction was from bottom to top here in this case, right? Because you see the steep sides that are shadowed here and then the shallow, gentle downstream part of that eddy here, okay? The next version of this are called tool marks, which are produced by objects that are being carried by the flow that interact with the bed, and these can be grooves or skip marks, for example. These are grooves in this case, and it could have been a stick or it could have been a pebble or something like that, or a poor shrimp who got entrained or whatever that is now rolling or sliding along the bed and cutting these marks, and sort of the orientation of these can tell you again that sort of plus or minus 180 direction of transport, but oftentimes with grooves it's hard to tell the direction. If there's a skip mark where it starts and then where you see the initial pit and then the direction that it's going, you can tell which specific direction, but typically you can only tell either it's going this way or that way, but you can rule out this way, for example, in this image. So those can be useful as well for determining flow directions. There are mud cracks. This is another bed form, or another, not bed form, sorry, another sedimentary structure that's common in the rock record. And these occur when wet sediment, wet muds shrink when they dry. And when it's complete drying, it's referred to as desiccation cracks. When it's underwater settling, you get mud cracks, but they're referred to as syneresis cracks. So when it's not actually, so when water is being expelled by the settling and not the drying process, that still can result in shrinkage, and I'll show images of that. That's referred to as a syneresis crack. So desiccation cracks is what's being shown here. These are in Death Valley. There's photos I took when I was a master's student doing my fieldwork out there. But you can see these are relatively deep. They're connected. Complete cracks where these polygon chunks of mud can then be at some later time either ripped up by a future current and deposited as what are called intraclasts or rip-up clasts, and we'll talk about that later, or it can be infilled with other sediment and preserved, and then you can get these preserved as mud cracks, desiccation cracks in the stratigraphic record, and they're fairly common to see that way. You can also see in this particular case raindrop impressions, which are super cool to find. That tells you unambiguously that this deposit was exposed subaerially, right? So it was exposed to the air at some point. So these might be lake sediments, lake bed sediments that have dried out and received rain. That tells you that they were lake bed sediments that sometimes were exposed to the air, which tells you that they were probably in a shallow environment, right? So that's why that's useful to know. These are what are called syneresis cracks. They're a little bit less interconnected. You can see there's sort of these little like triple junction type cracks that don't necessarily connect. And so this is kind of indicative of the fact that these may not have been fully dried, but in fact were shrinking because the water was being expelled as the mud settled on the bed, and water was sort of being ejected that way, and so it shrinks because the water was being removed from the mud, but it's not being dried, if that makes sense. So as it's compacting, all right. Those are very common in certain scenarios, and you can see there's sand coming up through here. So this was mud deposited on a sand bed, and that's often how you can recognize them in the record, is that distinction again between the grain sizes on the bed. And there's raindrop impressions, like I mentioned before, that can tell you again that this was a subaerially exposed environment. This is just a particularly beautiful example of those with mud cracks, raindrop impressions. The mud cracks are really thin here. You can see that they're lifting up, so these would be great candidates to be ripped up off of the bed in a future flow. Say the next rainstorm that comes by might rip these clasts up and deposit them somewhere else as mud chips. There are soft sediment deformation structures that can occur. So once a bed is deposited, different settling and dewatering processes, etc., can result in the sediment bed being modified after it's deposited. Very common versions of these are called load structures. There are addition pillow structures that are a function of fluidization of the sediment. And then there can be convoluted bedding and sand injections that can be associated with things like liquefaction that can occur due to, say, seismic movement or other dewatering processes, say, as a mass transport. If a deposit starts to move down slope, it can dewater very quickly and so forth. So what loading structures look like is when you have a coarse, it results from an instability in density. So if you have higher density deposits deposited on top of lower density deposits, right, then the high density upper layer tries to sink into the lower layer. This is common if you have deposition of, say, sand on top of mud, where the mud has a lot of water incorporated into it. It has a very high porosity and is very low density. Then you get a sand deposit on top of that. That sand, because it has lower porosity, is more dense, and it tries to sink down into the mud, and it does this by forming these load structures where the sand sinks down on these sort of, like, I don't know, cup-shaped features here, and the mud starts to sort of inject and squeeze itself upwards, right? Oftentimes this happens in a situation where there may be also mass movement. So the sand is coming from somewhere. Maybe that sand is being brought in by a current. And if that current is pointing in one direction, the mud that is now being loaded and squeezed up into the sand might get deflected down in the direction of transport, more or less. If there's a stress or a shear being imparted on that sand, then it's going to shear that interface, and you get what are called flame structures that point down shear, or down direction, if you will, down flow. I don't know if that's the right way to say that. You can get fluidization. This is a really cool process that happens where sediment can get mobilized by sort of intragranular flow. So grains can start to flow around other grains. This can often happen as a result of movement of pore fluids, right? So oftentimes that the pore fluid is trying to move upwards to escape as compaction and settling are occurring. And so grains that might be in the interstitial spaces between other coarser grains will start to become transportable and move through the grain framework and sort of get sort of depleted from some areas and sort of concentrated in other areas, which result in these sort of dish-like structures here, which it's hard to get a good picture of them because they're not typically very easy to see, but you can kind of see these depleted dish sort of areas here in this photograph here. And so you get some areas that have no fine particles, and then the areas where the fine particles got concentrated to, and these create these dishes. Okay. You can get liquefaction that can occur if you have water saturated sediments that basically change state, if you will, from a solid to a liquid state as a function of the increase in pore fluid pressure. So if the particles start to move relative to one another because they've been, say, impacted by an earthquake, or if they start to flow, right? If they're being moved down slope and they start to get transported in shear, the shear dilation can result in increasing the other way around. The increase in pore pressure that is associated with those particles moving, right, can result in that pressure sort of separating them apart a little bit, right? As you increase the pore pressure, you try and force the particles away from each other. And that can result in that pile of sand starting to move as a liquid. And this can happen in sort of in stages. It can happen locally, and you can end up with what's called convoluted bedding, where these were fluvial cross beds in this upper right hand image that would have been nice cross bedding like this, that have started to slump, right, and started to flow down a slope, presumably, right? And so you get this weird little flow structures that occur in what would have been, planar cross-bedded sands. Same thing here. You get convoluted bedding where there might be a permeability barrier as this fluidized sediment starts to try and flow, and it reaches some resistant trap somewhere. And so either that can start to become more convoluted in that region where the sediment was trying to flow, or it can eventually escape out, right? So you end up with really interesting structures that result from that, and they can get very complicated, but really all they tell you is that this sediment was fluidized. They're ooh-ah structures, but often not terribly useful in terms of interpreting the actual environments of deposition. There's sand injections that can occur when you get really localized high pore pressures in a confined area, like we talked about before. If there's some region of the sediment pile that is somewhat confined by overlying rock or overlying sediments, say you have sand that's confined by an overlying less permeable mud, As that sand potentially becomes fluidized by some process, say an earthquake, say, by just poor fluid movement, it can eventually break through and fracture that confining layer, and you can get sand volcanoes and sand dikes and sills, for example, in these images. Here's some sand volcanoes that have erupted to the surface, right? And then here is an example from, you can see in this muddy floodplain deposit, the sand dikes that have broken through as a function of the sort of fluidization of the sand bodies that were kind of trapped within that muddy deposit. Okay, so that's relatively common feature of liquefaction. And then finally, we'll talk about trace fossils and bioturbation. I'm not going to go into a ton of detail on trace fossils because we offer a paleontology course in this class where that's, or in this department where that is covered in a little bit more detail. Suffice it to say, if you're a sedimentologist or a stratigrapher, it is useful to understand what types of burrows and feeding traces and so forth can exist in different environments, because different types of creatures and different types of feeding habits occur in different, say, parts of the beach environment or different parts of the shore face. And by seeing some of these different features in the rock record, you can potentially pick out whether you're in an upper shore face or whether you're in a lagoon or something like that, right? And so I'm not going to go into too much detail on these, other than to say that there are a number of different ways in which you can classify and categorize the shapes of these feeding tracks and burrow morphologies and so forth. Okay. Can anybody guess? I'm going to leave this one out there for anyone to guess what this feeding trace or what this trace fossil is. This is from the Bonnet-Carré spillway again. Maybe we'll talk about it in our discussion next. If someone can guess what this one was, but it's a cool. This could be deposited someday as a trace fossil if sediment got buried on top of it. Right. But one thing that is important to note is, again, as I kind of mentioned, that we can classify different types of trace fossils based on the different types of environments that they might have formed in, and use those to, say, look at paleo trace fossil assemblages to say, well, I think I'm seeing a transition from these types of burrows down to these types of burrows in in my environment. That's telling me that I'm going from a sort of a shoreline to a sublittoral zone here, and then down into the abyssal zone if I see these, sort of more intricate feeding traces here. And again, I won't go into much detail on this, other than to say that these are things that are worth learning about if you're taking a paleontology course to become a sedimentologist, so that you can go out to an outcrop and you can see, oh, I see a scolitos type, burrow trace here. That tells me that I'm sort of in a sandy shoreline type of environment. Okay, but one issue, as with many sedimentary structures, one issue with bioturbation and trace fossils is that they can be formed by any number of different creatures, can result in the similar morphologies. And so one thing that's really important to note in this class in general is that it's oftentimes not just one feature and one feature alone that tells you what environment of deposition you're in. Oftentimes you're taking into account the whole of your observations, maybe not even just from one outcrop, but from multiple outcrops in the area, to build your picture of what kind of environment you're in. So say I'm looking at an environment that has dune scale cross stratification. Well, any number of environments, like a river or a tidal delta or a shore face environment might result in dune scale cross stratification. Okay, well, now I also see scolitos, so maybe that narrows it down a little bit, and so forth. So you're trying to take individual observations and view them as a whole to try and get yourself towards a consistent interpretation. And so that's sort of where we're going to go with much of the rest of this class. Okay. And like I said, trace fossils are no exception. Many of these trace fossils can be formed in different environments. Here's my favorite. What kind of feeding trace would you call this if you saw that out in the wild? I would probably look at that and think that it was an armadillo track or something, right? But in fact, it's just a Adobe Lab retriever going through and cruising along trying to scratch its face or something. So anyway, so after this lecture in the next weeks ahead, we're going to start talking about siliciclastic environments and environments of deposition, and pick out particular environments to talk about what kinds of processes occur in each environment and what types of sedimentary structures and facies assemblages or the combination of sedimentary structures that you might expect to find in any of these different environments. And so we're going to start off with glaciers next week, and we'll just do glaciers for next week because it's a short week because of Mardi Gras. All right.